Hello friends, welcome back to Relief Tutorials. In previous lecture we have discussed about Euclid's axiom. Today we are going to discuss about 5 postulates of Euclid's. So Euclid's postulate, first postulate, a straight line may be drawn from any one point to any other point. Clear? So here one point, if I say A, here A, this one point is A, then this is B. So a straight line may be drawn from any one point to any other point. It means at least one straight line passes through two distinct points. But it does not say that there cannot be more than one such lines. However, Euclid has frequently assumed that there is a unique line joining two distinct points. See, this postulate can be also explained in the form of an axiom. See, it is universal truth. You know what our axiom I have discussed yesterday. It is taken as a granted without any proof. So here we can say that given two distinct points, A and B, given two distinct points, there is a unique line. There is a unique line that passes through them. So this we can take as a axiom. Means one and only one line can be passed through two distinct points. See, how can a student see this? Suppose I will take one point P. This point I have taken P. I will take another point here Q. So we know that now see here there are two distinct points P and a Q. So we have to prove that there is a unique line passing through P and Q. See now, number of lines passing through P, we can pass many lines passing through P. See, this is one line passing through P, this is another line passing through P, this is another line passing through P, this is another line passing through P. So there are different distinct many lines that passes through P. So the number of lines passing through P, which also passes through Q, passing through P, which also passes through Q. So I can say this line passing through P also passes through Q is only one, that is PQ, or the number of lines passing through Q. See, through Q you can pass many lines. You can pass many lines through Q. See, all this line passes through Q. So the number of lines passing through Q, which also passes through P, is again only one. See, number of lines passing through P which also passes through Q is only one. Number of lines passing through Q which also passes through P is only one. That is PQ line. Thus, the above statement is self-evident and so it is called axiom. See, this is self-evident, no? There are number of lines which is passing through P. And line passing through P and Q is one. And there are number of lines passing through Q. Passing through Q and P is only one, that is line PQ. So this is a statement is self-evident statement, so we can consider it as a axiom. So this is first postulate which can be also considered as axiom. Given two distinct points, there is a unique line passing through this point. So one line, only one line can be passed at a time through two distinct points. Clear? So this is postulate 1. Now we will discuss postulate 2. A terminated line. A terminated line can be produced. So you have to remember these postulates. A terminated line can be produced indefinitely. Indefinitely. See, if I say one terminating line, this is terminated line, A, B, this is terminated. Terminated means it is not extending in both the direction. This is called terminated line. Terminated line means line segment AB. So this can be extended indefinitely. See, this can be extended indefinitely in both the directions. This is postulate 2. So, terminated line can be produced indefinitely. I told you what is the difference between axiom and postulate. See, this is confined to geometry postulates, all these facts are. Whereas axiom, I told it is applicable everywhere. It is a accepted fact. It is a granted fact. Now we have seen postulate 2. Now we will discuss postulate 3. Postulate 3. What is postulate 3? See. Postulate 3, a circle can be drawn with any center and any radius. A circle can be drawn. A circle can be drawn with any center. With any center and any radius. You know, in order to draw circle, we require two things, center and radius. So, you can draw a circle with any center. See, these are center I have taken. For example, this is center P, this is center Q. So, you can draw a circle with any center and any radius. Suppose I take this as a radius. So, this circle can be drawn. Suppose I here take this as a radius. So, a circle can be drawn with any center and any radius. This is postulate 3. Very easy. Now, postulate 4. Postulate 4. All right angles are equal to one another. All right angles. All right angles are equal to one another. Are equal to one another. So, all right angles are equal to one another means this I have taken one right angle. ABC. This I have taken another right angle. This is PQR. You take another right angle. This XYZ. So, all these right angles are equal to one another. So, that we can say angle ABC is equals to 90. Angle PQR is equals to 90. Angle XYZ is equals to 90. So, therefore, we can say angle ABC is equals to angle PQR is equals to angle XYZ. So, all right angles are equal to one another. So, two postulates we have discussed. Postulate 3, a circle can be drawn with any center and any radius. All right angles are equal to one another. See these two postulates. Now, postulate 5. Postulate 5. What is that? See, I will explain by diagram. I will draw two lines. This is one line. This is another line. So, these are two lines. If I say clear, L and M, two lines. And I will draw one more line, N. So, now you see here, this angle I will take, this angle I will take. They are acute angle. Generally, mere by observation, you can tell, yes sir, they are acute angle. If I say this is angle 1 and this is angle 2. And here, if angle 1 plus angle 2 is less than 180, it is less than 180 degree. So, now, this two line L and M, and this is line N which falls on L and M, which falls on L and M, and these two angles are less than 180 degree, and if you extend these two lines, then naturally what happens here, they will intersect. Have you got it, friends? So, what our postulate says, if a straight lines falling on two straight line L and M, see a straight line N, this is falling on two straight line L and M, makes the interior angle, these are the interior angle on the same side of N, taken together less than two right angles, then the two straight lines if produced, then these two straight lines are produced. Clear? If they are produced, see these two straight lines are produced indefinitely, will meet on the side on which the sum of angle is less than 180 degree. So if you produce these two lines indifferently in both the direction, then they will meet on the side where the sum of the angle is less than 180 degree. Here on other side, you know, sum of these two angles is greater than 180 degree. Here these two lines will not meet. They will never meet. See, they are going in different directions. See, these two are going in different direction. This way. So here they will never meet. Have you got it? So this is postulate 5. So if a line falling on two straight lines, here this line N is falling on two discrete line L and M. So interior angles are formed. Okay. Now sum of angle 1 and 2 is less than 180 degree, and if you extend these lines, then they will meet on that particular side of line N. This is postulate 5. Have you got it? See, up to postulate 1 to 4 they are quite simple and they are taken as self-evident truth. They can be considered as axioms. So now what Euclid did, using these axioms, postulates, definition. So using all these postulates, axioms, postulates and definitions, Euclid proved other result. Other results. Then using all these results, he proved some more results. Using deductive reasoning. See, there are two types of reasoning that we will learn in higher standard, in 11th standard: inductive reasoning and deductive reasoning. So what that fellow has done, using all these axiom and postulates and few definition, he has proved some result. Using these results further, he has proved some further results using deductive reasonings, and all these results or statements that were proved. So the statements which were proved are called propositions. They are called propositions or theorems. You see the path followed by Euclid. He has compiled all the informations from all the civilizations and he has compiled it into a book called Elements. He divided this book into 13 chapters. In first chapters he has given few definitions. Based on this definition he has proved some self-evident truths which are called axioms, and then which were confined only up to geometries, they were called postulates. And using these axioms and postulates, that fellow has proved some few more results. Using these results, he has proved further few more results using deductive reasonings. So all these statements that were proved using axiom, postulates and results are called propositions or theorems. And you know that he has declared how many propositions? Nearly about 465. 465 propositions were deducted in a logical chain using all these axioms, postulates, definitions and theorems. And all this geometry is called Euclidean geometry. Have you got it, friends? All this geometry is called Euclidean geometry. Now, okay, we will prove few theorems, which were proved by Euclid's theorem. Two distinct lines cannot have more than one point in common. So two distinct points cannot have more than 1 point in common. So here this can be given. See, first we write given. What is given? Two distinct lines are given. Two distinct lines L and M. See, so two distinct lines, two different lines cannot have more than one point in common. If they have any point in common, it will be only one point. More than one point cannot be in common between two distinct lines. So here it is given two distinct lines L and M. So okay, I will draw two distinct lines L and M. See, this is one line, we will draw L. This is another line, we will draw M. So these are the two distinct lines L and M. Now you have to prove, what you have to prove? See, you have to prove L and M have only one common point. Only one common point, that we have to prove. So now proof. So first we will suppose that these two distinct lines intersect at two distinct points. Then we will say that our assumption is wrong. Okay. So suppose what we will see, proof, let us assume, see, we are going to prove this statement by using axioms and postulates. As a result, it is termed as theorem. So theorem is a statement which requires some logical reasonings and some evidence to prove it. So now you have realized what is the difference between axioms, postulates and theorems. So now let us assume that two lines L and M intersect at two distinct points. Say P and Q. These are the two distinct points where these two lines intersect. So then we can say, then L contains both the points which P and Q. Why? Because they intersect at two distinct points. Clear? See, for example, if I say if two lines intersect at one point, if I say this way, see, if two lines, see, this is one line and this is another line. If these two lines intersect at point P, for this is L, this is M. So I can say P belongs to L. P is a point on line L and P is also a point on line M. So P belongs to both the line L and M. But in our case, we have supposed that the two lines intersect at two distinct points P and Q. So line L contains both the point P and Q, and also M contains both the point P and Q. But from axiom, we know that one line can pass through two distinct points. But from axiom, we can say, or we know that only one line can pass through two distinct points. We have seen just now today's lecture. If you know that through two distinct points we can pass only one line, that we have discussed in postulates. Clear? What was postulate? You know, postulate 1 we have discussed that only one line can pass through two distinct points. Clear? Do you remember that? So what was our postulate 1? See our Euclid's postulate 1. See what was postulate 1? I told you postulate 1 can be treated as axiom. I have explained you this. Okay. What was that? Given two distinct points, there is a unique line that passes through them. See, here we have seen this is the line PQ which passes through P and Q. There is no other line other than PQ which passes through two distinct points. So given two distinct points, there is a unique line. Do you know what do you mean unique? Unique means one line, only one line. So through two distinct points, we are able to pass only one line. This is postulate 1, or we can treat them it as a axiom. So we can say, but from axiom or postulate 1, we know that only one line can pass us through two distinct points. But here you know that L contains both the point P and Q, and M also contains both the point P and Q. But I told you that there is only one line which can pass through two distinct points. If it is L, then how it can be M? Why? Because it is also passing through two distinct points, but our axiom says that only one line can pass through two distinct points. But here both L and M, they are passing through two distinct points. It means these two lines are same. We can say So therefore L is equals to M. Clear? So our assumption is wrong. Our assumption is wrong. What was our assumption? L and M have only one common point. Our assumption is, let us assume that two lines L and M passes through two distinct points. So our assumption is wrong. So hence two distinct lines cannot have more than one point in common. So we can say hence two distinct lines cannot have more than one point in common. In other words, we can say if two distinct lines intersect, they do only at one point. Clear? So if two distinct lines intersect, they do only in one point. See, here I have told this, two distinct lines intersect at a point means they do only in one point. Two lines cannot be intersect at two distinct points. See, can you say here, see sir, here two lines are intersecting at two distinct points here. These two distinct points, point of intersection. But you know, this is line L, this is M. I can say line cannot bend. No, it is a straight line. So it is not possible at all. If two lines intersect, they do only at one point. Clear? So this we have proved. This theorem we have proved by using axiom or postulate 1. So in this way, Euclid has proved some statement. This type of statement Euclid has proved. The two distinct lines cannot have more than one point in common. So this statement was proved by using some axioms and postulate. Is it clear? And he has deduced some result. As a result, it is called theorem. Clear? Now, so this is theorem. Now we will discuss some basic definitions. See, this is not mentioned in your textbook even though. If I say line segment, what is the? We'll discuss this line segment. So a part of a line which is bounded by two distinct points is called a line segment. So line segment is nothing but it is a part of a line. See this A, B. I can extend this way so it will become line. So this line segment AB is a part of a line. As a result, it is called segment of a line. Segment of a line means part of a line. The name itself suggests line segment. Cutco. Segment means cutco. It is a part of a line. So line segment is nothing but it is a part of a line which is bounded by two distinct points here A and B. So it has two end points. That is called line segment. Interior point of line segment, if you want to explain. Interior point of line segment. See, interior point of a line segment. What is interior point of a line segment? See, if I do this is line segment AB. Now interior point of a line segment. If I take here point P. So P is called an interior point of line segment AB if P lies between A and B and P is neither A nor B. So P is not equal to A and P is not equal to B. It is somewhere in between A and B. That is called interior point of a line segment. Clear? Now, third definition we will discuss, that is congruence of line segment. Congruence of line segment. So two line segments are called congruent if the trace copy of one can be superposed on the other so as to cover it completely or exactly, and it is denoted by, see here, two line segment AB and CD is congruent, I can say. This is line segment AB. Okay. And this is line segment, red colors. This is line segment CD. So these two line segment AB and CD are congruent. Why? If the trace copy of one can be superposed on the other so as to cover it completely or exactly, and it is denoted by line segment AB is congruent to line segment C. See, they are exact copy of one another. Clear? Two line segments are congruent. We can say this way also. See, this is line segment AB and this is line segment CD. It is not necessary they should be superimposed on one another. Okay, the length should be same. So that is called congruent line segment, and we can denote that AB is congruent to CD. Now opposite ray, already this we have discussed lines and angles. Opposite ray, so you know two rays AB and AC are said to be opposite ray if they are collinear and point A is the only common point of these two rays. Opposite rays, see here. This side say A, this side say B, this side say B. So this is ray AB and this is ray AC. They are opposite ray and these three points are collinear points. So I can say ray AB, see this is not ray AB and ray AC. They have one common initial point, that is A, and all these three points are collinear points. Then we can say these two rays are opposite rays. And you know what are collinear points? These are collinear points. Three or more than three points are said to be collinear if they lie on the same line. See BAC, they are lying on the same line L. So we can say BAC are collinear points. Clear? Now intersecting lines. Do you know what you mean by intersecting lines? These are collinear points. Collinear points. So points are collinear if they lie on the same line. Now intersecting lines. See, these two lines are called intersecting lines. They have one point in common. Suppose P. So two lines have a common point. Okay, if two lines have a common point, then they are called intersecting line. And the common point is called point of intersection. This P is point of intersection. This line L and M, they have a common point. So P belongs to L and P also belongs to M. So this is a common point, belongs to both the lines. And this point is called point of intersection. Clear? So this is intersecting lines. Now we will discuss concurrent lines. What do you mean by concurrent lines? L, M and N. These three lines have a common point P. If two lines have a common point, then they are called intersecting lines. If three or more than three lines have a common point, then they are called concurrent lines. So here L, M and N are called concurrent lines. Clear? So three or more lines intersecting at the same points are called concurrent lines. If two lines have a common point, they are called intersecting lines. So these are intersecting lines. These are intersecting lines. Clear? So if two lines have a common point, then it is called intersecting lines. If three or more than three lines have a common point, then they are called concurrent lines. Clear? So this we have discussed few definitions. Now, equivalent version of Euclid's fifth postulate. This is very important topic. See, we are going to discuss equivalent version of Euclid's fifth postulate. Clear? So we are discussing equivalent versions of Euclid's fifth postulates. What is that? See, I will draw here. So there are two lines. Euclid's fifth postulate is very significant in the history of mathematics. It is very important, this fifth postulate of Euclid's. There are several equivalent versions of this fifth postulate. One of them is Playfair's axiom. What we are discussing? Playfair's axiom. See, this is equivalent version of Euclid's fifth postulates. They are almost same. Do you know what is equivalent? Nearly same. So equivalent versions of Euclid's fifth postulates, there are many versions. but most important versions is play-fair axiom. See what it says: for every line L and for every point P not lying on L. See, I take this line L and this is a point P. So this is line L and P is not lying on line L. Okay, so for every line L and for every point P not lying on line L, there exists a unique line. There exists a unique line M passing through P and parallel to L. See this, for every line, you take any line, not for particular this line only, for every line L and for every point P not lying on L, there exists a unique line. There exists one line only, one line. There exists an unique line, that is M. There exists an unique line M passing through P and parallel to L. See, these lines are not parallel to L. They are passing through P, but they are not parallel to L. Clear? So, there is only one line. You can do again many lines. See, all these lines, what happens? Red color line, they are passing through P, but they are not parallel to L. So, there will be only one line. Out of all these, there will be only one line which passes through P and parallel to L. So, this axiom is called play-phase axiom. Okay. So, for every line L and for every point P not lying on L, there exists a unique line M passing through P and parallel to L. Clear? Or in other words, we can say two distinct intersecting lines cannot be parallel to the same line. See this line, you can say M, and for this example P, M and P. See, M and P, they are intersecting line. Clear? So we can state that two distinct intersecting lines cannot be parallel to the same line. So these two lines, M and P, they cannot be parallel to L. Both. Either M can be parallel or P can be parallel. But these two lines cannot be parallel to the same line. We can say in another way, say these are two lines I have drawn. Clear? These two lines, M and N. So these two lines cannot be parallel to the same line at a time. If I do only one line, see here, N, then M is parallel to N, but P. M is parallel to P, but N is not parallel to P. So two distinct intersecting lines cannot be parallel to the same line at a time. Only one line can be parallel. Both cannot be parallel to the same line at a time. Both can also not be parallel. Here, one line is parallel, M is parallel to P, but N is not parallel to P. If you do this way, see, one line here, M and N and P. Here both lines are not parallel to P. If you extend them, they will intersect to this line P. If you extend M line, it will intersect to line P. So it is not necessary that both lines should be parallel. But one fact is clear. See, this both lines cannot be parallel to P. But here we see here, out of these two intersecting lines, two lines are not parallel to the same line. One line can be parallel. So what is equivalent versions of fifth postulates of Euclid is that for any line L and for any point P not lying on L, for any line L and for any point P not lying on L, there exists a unique line M passing through P and parallel to L. So this will be only one line. Out of this many lines, there will be only one line which will pass through P and will be parallel to L. Clear? So this is equivalent version of Euclid's. Clear? See now. So now, all attempts to prove fifth postulate of Euclid, all attempts to prove this fifth postulate, to prove as a theorem, failed. So many attempts were made to prove this fifth postulate as a theorem, but it failed. All attempts were failed. Clear? But these efforts have led to a great achievement. So many people have tried to prove this fifth postulates of Euclid as a theorem by giving many logical reasoning, but they failed. But these efforts have led all these efforts has led to great achievements, the creation of several other geometries. Many other geometries were created. Okay, and these geometries are different from Euclid geometry, so they are called non-Euclidean geometry. Non-Euclidean geometry. Have you got it? So what happens? This fifth postulate, many mathematicians, they have tried to prove this fifth postulate as a theorem by giving many logical statements and reasonings, but all these attempts were failed. They are not able to give proper reasonings. But this effort led to the creation of many other geometries, and these geometries were totally different from Euclidean geometry, and they are called non-Euclidean geometry. You know, the geometry of universe in which we live are considered as a non-Euclidean geometry, and it is called spherical geometry. It is also called spherical geometry. Spherical geometry. You know, these Euclidean geometries are valid only to the figures in the plane, but on the curved surface it fails. So this is the limitation of Euclidean geometry. Limitation of Euclidean geometry. What are the limitations of Euclidean geometry? It is valid only for the figures. It is valid only for the figures in the plane. Plane means like paper. See, figures on the paper, two-dimensional figure only it is valid. If you take a ball, see, you can't draw a ball, complete ball on a paper. It is a three-dimensional figure. It is a sphere. So here, in order to explain sphere properly, he failed. So such geometry is called spherical geometry. So that is the limitation of Euclidean geometry. It is valid only for the figures which are drawn on the plane, that is on the blackboard, two-dimensional. Clear? So in the plane, but not on the curved surface. On the curved surface, it fails on the curved surface. So this is the biggest limitation of Euclidean geometry. So I hope you have enjoyed this theory part of this chapter. In next lecture, we are going to do our exercise 5.1. Okay. Till then, goodbye.